Okay. Let's see. Have we got those quizzes ready?
Sure.
Good. Be looking up any homework questions if you have them. We had done 2-3 and part of 2-4 last time. Any concerns about those? Did you find any you'd like to look at?
Number 19 on page 112.
If I were to graph that on the calculator, let me show you what would happen. Let's see. I'll graph that. The only part I wouldn't be able to graph on the calculator is the middle piece, which is when if x is 1, y is 0, I'll just have to sort of point out that point. But we have y equal x if x is less than 1. So I put that in parentheses. If x is less than 1. Oops. Less than is 5. And the other piece that we could graph is negative x plus 2 if x is greater than 1. Okay. If I graph those two pieces on a standard window, here's the first piece, there's the second piece. The one point that we can't graph is if x is 1, y is 0. So there should be an open circle at that point and a closed dot right on the axis. Okay? In other words, it should look like this. It's looking something like this. I still am not liking the orientation. If you'll bear with me just a second. After all that jiggling around, I think it didn't want to write where it should write. Right. Now it should write a little better. Okay. So I will erase that. And we'll say that's 1. It sort of looks like this on your calculator. Whoops, if that's 1. But there should be an open circle there and a closed circle on the axis. Okay? So what they're asking you in number 19 is what is the limit as x approaches 1? Okay? The limit as x approaches 1. Actually, I wouldn't even need that dot because it's going to approach the same value from both directions, right? So I'll pull the calculator back up. If x gets closer and closer to 1, what's y going to from both sides?
2, 1.5, something like that.
Is y going up to 1? Look at the pieces. It looks like in the first one, if you get close to 1 in that first piece, it goes to 1, doesn't it?
Yeah.
If you put 1 in that last piece, negative 1 plus 2 is 1. So both sides go to a y value of 1 at that point, correct? So they approach the same value, so that limit would be 1. Approaches the same value from both sides. That little open circle at the point.
So why wouldn't it be 0?
The actual value when x is 1, y is 0. But see, if you get closer and closer and closer to 1 on the x-axis, the y gets closer and closer to that open circle at the point up at 1. And if you come from the left side, you get closer and closer and closer to 1 on the x-axis. The y gets closer and closer to 1 on the y. Look at my table, if that helps. What if I said this? If I use this function and I went to my table, if I put in, let me delete some of this. Okay. What if I put in 0.99? It gets close to 1, doesn't it? If I put in 1.01 from the right-hand side, it's 0.99. So it's getting closer and closer to 1, isn't it? From whichever way I approach 1. But the function itself, if I let x equal 1, it's 0, isn't it? So, but it gets closer and closer to a y value of 1 for both sides. So if I look at that graph again, the closer I get to 1 from either side, that y value goes to that point, which is positive 1. That would be my limit if it approaches.
So how do you know, like the others, I mean, they're telling you that 17a is equal to 0, 18a is equal to 3, but this one here it says a is equal to 1.
Yes.
So,
see, the instruction said the limit as x approaches a, so as x approaches that a value 1, what does the y go to? And in this case, I guess it was a little confusing, because as x gets close to 1 from either side, the y goes up 1 unit up. So that was basically the same value, wasn't it? So maybe that's what.
Put 1, 0, 1.
What's that?
I was wanting to put 1, 0, 1. Three
Well,
different
see,
values.
what happens is the way I listed the function was in y1 and y2, and any time that it's not defined for a certain piece in your table, it shows up as a 0, doesn't it? So you shouldn't really look at those zeros. You should just look at that value. If I put in 0.99, which is very close to 1, but from the left, it gets very close to 1, doesn't it? And if you get close to 1 from the right-hand side, 1.01, it gets very close to 1. So that's the limit it goes to.
you can't base your answer off of just that function showing.
Yes.
Look,
If you look at the first piece in that function, let me write it up here. Let me see. F of x was equal to these three pieces. It was x, it was 0, and was it negative x plus 2, is that right? For x, it was the pieces were
X less than 1.
less than 1,
Equal to 1.
equal to 1.
And x is greater than 1.
So think of it like this. If I approach from the left-hand side a number below 1, I would put it in this piece. Well, as I get closer and closer to 1, that approaches 1, doesn't it? If I let x get close to 1, y would be close to 1. If I put a number larger than 1, like 1.01, 1.001, and I get closer and closer from the right-hand side back to 1, where does that go? If I get very close to 1, that goes to 1 also. So this piece, if x gets close to 1, approaches 1. This piece, if x gets close to 1, it approaches 1. Since they go to that same point, the limit is 1. Even though the function is defined to be 0 at that point, the limit is y equal 1. So, okay. It's easier to see in one like 18, where if you let x get closer to 3 in those pieces, what's the limit? In the first piece, if you let x get close to 3, it's 2, isn't it? In the other piece, the limit is negative 6 plus 8, which is 2. So the limit would be 2, wouldn't it? Both sides approach 2. And that was a little easier to see. But since the answer was 1 and you were approaching 1 on the x-axis, it seemed like all the same number, didn't it? So, but that's what I wanted you to see, that if I get closer from the left to this 1 value on the x-axis, the y goes up to 1. If you get closer from the right on the x-axis, the y value goes up to that point, which is y equal 1. So that would be your limit. Any others?
Try 61.
61. (61) says the limit as x approaches 1, 2x minus 2, whoops. 2x minus 2 over x cubed plus x squared minus 2x. I think we're going to be able to get away with this one just by factoring.
Mm-hmm.
So if I factor the numerator, and then I factor, all I can factor out here is an x first, x squared plus x minus 2, and then go one step further, I think that's going to factor into that x plus 2, x minus 1. And then the x minus 1s will cancel. And if I let x get close to 1 now, that would be 2 over 1 times 3.
Mm-hmm.
2/3 would be my limit. Because before, if I just let x get close to 1 in this, it's a 0 denominator. It's indeterminate, 0 over 0 in fact. So that's the one where we have to algebraically work on it to make it work. Okay? It's a good one. Any other concerns before we finish this section? All right. What we didn't have time to address last time, we did some limits like that. We didn't take time to look at the limits as x might go to infinity. Okay? So first of all, just to get us used to this idea, what if they say in number 64, do you see that graph? They give me a graph, and they say it looks something like this. They want me to find the limit as x approaches infinity of f of x, and the limit as x approaches negative infinity of f of x. You tell me, if this is my graph of f of x, if x gets larger and larger and larger without bound, where's the y going? If I had an x value way out here, wouldn't the y value be way off the board up in the sky? Yeah. So you know what the limit would be for that one? It would be infinity. What if you let x go to negative infinity? Where's y going? Down forever. What do I call that? That's it. Okay? Compare that one to another good example, 66. I like this one. Same question. If you have this new function f of x, and they say the graph looks like this, and they say that that is 1. Okay? And let me put little arrows on here so it looks even better. All right? Let's ask the same questions. What is the limit as x goes to infinity of f of x? And what's the limit as x approaches negative infinity of f of x? Exactly. If x gets larger and larger and larger, that seems to never go beyond 1, does it? It approaches 1. If you get your negative numbers larger and larger to infinity, looks like with that asymptote they drew in there, I think you're right. That approaches 1. It's closer and closer and closer. We're not sure it ever gets there. Okay? What would you say about 68? Look at that graph. 68 looks like this. One piece is doing this, and the other piece is doing that. And this is at 1.
1 and 0.
So let's ask the same question. Limit as x approaches positive infinity of f of x. If I get larger and larger to the right, the y is going where? Good. But what about if I go to the left for it? The limit as x, sorry about that, limit as x approaches negative infinity. That seems to be going up forever. We don't know where it would stop, so you would say positive infinity. Does that make sense? This seems to never go beyond 1. The way they drew that little asymptote there, like it was approaching. But this one seemed to be increasing forever. So the further out I went to the left, it would keep going up forever. Okay? Very good. Now here's the big idea that I need you to get before we can do some other problems like this with the infinities. Okay? See if this makes sense. The limit as x approaches infinity of k over x to the n, if k is a constant, what would you think that would be? What if this x gets larger and larger and larger? Yeah. If that's like a 2 or a 7, some constant, but this is like a million, then a billion, then a trillion, that fraction gets smaller and smaller and smaller towards 0, doesn't it? That limit is 0. Same thing, the limit as x approaches negative infinity of some constant over x to some power. I don't care what that denominator is, if it's negative 1 trillion, but the numerator stays 2 or stays 7, if that's a huge positive or negative number, that keeps getting closer and closer to 0, doesn't it? The larger that denominator gets, the smaller that fraction is. Okay? That's going to help us do several problems coming up in the next few. When you see one like this, I hope you will think of this rule. A real example of it would be like if I said, what's the limit as x approaches infinity of 1 over x to the third? What do you say? 0. That could be any number. X to the first, x to the 5th. It would go to 0, wouldn't it? Because that denominator is getting huge. The numerator is not doing anything. So it's approaching 0. And you could see it from a graph. What if I just graphed this one for you? What if I said, what's the limit as x approaches infinity of 1 over x? And you already told me it's 0. Look at the graph mode. If I just graphed, let me clear this out. 1 over x, 1 divided by x, standard window. As x approaches infinity, what's y doing? Going to that x-axis, going to 0. What if x goes to negative infinity? What's y doing? It's coming up to 0, isn't it? Approaching 0 from below.
What if your denominator is negative x to the n?
You have to rationalize.
Say that again.
What if your denominator is negative x to the n?
negative x to the n or x to the negative n?
Negative x to the n.
So if I had negative x to some power n, could n be a 3 or a 2? Now, you're right, if n is a negative number, that would shift it back to the numerator, and it would be a different answer. But this, if it were negative, that would just be the same thing. Just look at this. What if I put 1 over negative x? Look at this. Look at your graph. What would that do to my graph if I put a negative in front of that? Reflected in the what from college algebra?
In the
X-axis. So look at this. If I put negative 1 divided by x, look at my graph. As x goes to infinity, it's still going to 0, isn't it? And I don't care if I put a power. If I put a power on the x, right, it's still going to do the same thing. What if I put an x squared here? What happens? As x goes to infinity, where is it going? 0. As x goes to negative infinity, where's it going? 0. You buy it? Good. Okay. That's what this is saying. Okay. And here's how we're going to use that. What if I asked you to evaluate a good one to start with is one that I'm going to make up. Okay. What if I said this? The limit as x approaches infinity of 8x minus 2 over 5x minus 3. Think about this. When you say x approaches infinity, aren't you thinking x is a million, a billion, a trillion, on and on and on? If x is a million, a billion, a trillion, are these numbers going to matter?
No.
No. What is 8 billion over 5 billion?
8 over 5.
That's your limit. Okay? That limit is going to be 8/5. But you know how we could get there without actually just having to reason? Here's the rule I'm going to use. If you have one of these limits that go to infinity or negative infinity, here's the rule I'll give you. Divide each term by the highest power of x. The highest power of x. Let me write that whole bit. In the denominator. That's what I'm going to ask you to do for any of these to make it easy to evaluate. What's the highest power of x in the denominator?
1.
1. You know what I'm going to do to this fraction then? Exactly what that says. I'm going to divide this by x, that by x, that by x, and that by x. That's legal, isn't it? Isn't that algebraically sound if I divide everything by the same number? Assuming x is not 0. Can you tell me what that new expression is if I do that?
8 minus 2x over 5 minus 3x.
Now, if I use those properties of limits we studied last week, to where I could take the limit of the numerator and the denominator and each piece of that if it's added or subtracted, what's the limit of this that we just erased off the board? If I said the limit as x goes to infinity, 0. What's the limit of that as x goes to infinity? What is left? 8/5. Isn't that great? That's an easy rule, isn't it? If you're trying to find a limit as x goes to infinity or negative infinity, use this little trick to divide out that highest power of x downstairs in the denominator. Then you can use that rule piece by piece, and anything that has an x in the denominator, or an x to some power, it goes to 0. Then you see what your limit is. I love that. But it makes just as good sense saying, in the original form I wrote it, if x is 1 billion, these numbers don't matter. 8 billion over 5 billion is 8/5. Right? Now, the reason I showed you that one first, I want you to try 74 using the same idea. Look at 74 on page 113. 74 says the limit as x approaches negative infinity of 4x squared minus 1 over x plus 2. If I use that little trick that I just erased, what would I do to all these parts? What's the highest power of x in the denominator? So I'll divide by x over x over x over x. What does that simplify to? 4x minus 1 over x over 1 plus 2 over x. Do you agree with that? Well, I agree that this and this go to what? 0. So those are gone. But what if 4x goes to negative infinity? Where's that going? Negative infinity. That one didn't cancel out to a 0, did it? Because there was no x in the denominator. So that tells me that that would go to negative infinity. Wouldn't it? And if you think about it, basically you would have, these numbers wouldn't matter, but if x got larger and larger and larger, you would have 4 times negative 1 billion squared over negative 1 billion. So that keeps getting smaller and smaller and smaller, doesn't it? Goes to negative infinity. And you could probably graph that to see it too if you wanted to.
So on that second step right there, all you're doing is adding and subtracting numbers.
Yeah. Once you divide by that highest power of x in the denominator, anything that has an x denominator, that goes to 0, doesn't it? So that would just drop right out, wouldn't it? And then I have left 4x. Well, if now I take the limit as x goes to negative infinity, that would go to negative infinity, with 4 times negative infinity. Okay.
Do you have any examples where it wouldn't be 0 as the limit on the second part?
Yes. Let me show you. Let's see. How about 76? You try that one and you see what you decide. 76 says the limit as x goes to infinity, 2x squared plus 3x plus 1 over x to the 4th minus x squared. If you use that little rule I gave you, what are you going to divide everything by? X to the 4th is the highest in the denominator, right? So if I divide everything by x to the 4th, let's look at it. Okay, that expression becomes 2 over x squared, 3 over x to the 3rd, 1 over x to the 4th. What's downstairs? 1 minus. Okay. Tell me what all of these that I'm circling are going to go to. So what does that leave me? 0 over 1, you're right, it's 0. If you let x go to infinity, all the fractions I circled approach 0. And that leaves me 0 upstairs over 1 downstairs. And that goes to 0. Think about how that makes logical sense. In the original problem, if you had an x squared up here and an x to the 4th down here, if x goes to 1,000,000, 1,000,000,000, isn't this x to the 4th going to make the denominator huge, a lot faster than the numerator? So that gets to be a larger denominator. It goes to 0. Okay? I like that. Probably the best example I could give you will be in your homework, will be like 75. Could you almost estimate what you see 75 going to if you divide everything by x to the third? Everything would go to 0 except 3 over 1, wouldn't it? Would that be a limit of 3? Would that be good? If I divide in 75 everything by x to the third, that leaves me 3, and then a fraction over 1 over x to the third. Everything goes to 0 except 3 over 1. You think? Okay. I guess the moral of the story then, even if you don't want to use that rule, if I have a limit like this that goes to infinity, and I had could you tell me what the limit is without doing much at all?
2 over 5.
If I divide everything by x squared, everything would go to 0 except this would cancel and leave 2/5, wouldn't it? That's what I'm getting at. The biggest mistake people make on these is they forget this only works if it's infinity or negative infinity you're approaching. I'll have a 2 or a 3 here, and people remember that, and they'll start dividing everything by x squared. If I said what's the limit as x approaches 1, you could just plug 1 in there, right? Unless there's a 0 denominator. So that only works for infinity or negative. So you'll let me know how those go at home when you try some. But that gets us ready to do some of the word problems on 113. They have some interesting ones, I think. What do you think of this? 82. 82 says, population of a certain breed of rabbits introduced into an isolated island is given by P of t is 72 over 9 minus 2. T is in months. They say T is only good for, actually, the interval it's good for is 0 to 9 months. No, other way. Bracket, parentheses. Bracket, okay? Find the number of rabbits initially at t equals 0. If t is 0, what is that? How many rabbits?
8.
72 over 9 is 8 rabbits. B, show that the population of rabbits is increasing without bound. Okay? Well, basically what we want to find is the limit as t approaches 9. We can't actually get to 9 because that's undefined, isn't it? Okay? Well, think about if you graphed it. 72 over 9 minus t. 72 divided by parentheses 9 minus t. Okay? If I graph that, just on a standard window, let's see what I can see. And I'll zoom out once. That's what I wanted to see. Do you see if this is 9 rabbits, what happens as you get closer and closer and closer to 9 from the left? Where's that population going? Infinity. If you weren't sure of that, couldn't you go to the table and say, what happens, let me delete, what happens at 8 months? What happens at 8.5 months? What happens at 8.9 months? 8.99? Do you see what's happening? The closer I get to 9, it's shooting up forever, isn't it? If I kept putting 9s there, that's going to be some huge number, isn't it? So what do you say? I would say this limit is what? If you get close to 9 in this, the limit is infinity. Okay. Part C is what we just did, right? Sketch the graph. They said the phenomenon is referred to as doomsday situation. Infinite number of rabbits, look out. You know? So, I like that. Another good one that makes perfect logical sense is 84. Good one. 84. The concentration of a certain drug in a patient's bloodstream hours after injection is given by this. C of t is 0.2 t over t squared plus 1. Okay. Evaluate the limit as t goes to infinity of that function and interpret your result. If I use that same little device that I used on the other ones that we went to infinity, what would I do here? So that would give me 0.2 over t, 1 plus 1 over t squared. If I reduced it, what does this go to, and what does that go to? Yes. Yes. Now tell me that that makes perfect sense. As time gets larger and larger and larger, what happens to that drug in your bloodstream? Hopefully it leaves, right? Hopefully it goes to 0 or you're in trouble, right? So, okay. That one makes good sense to me. All right? Good? Okay. The ones I want you to try from this set, here's the whole assignment. We'd already done part of it. Let me write the whole assignment up. Page 111 and 112. Make sure you can do 1 through 7 odd, 17 through 67 odd, and then 73 through 85 odd. Those are all the ones I'm interested in from that section. Even though we're going a little further in the notes, make a note here that we are ready for our next quiz Monday. Okay? Quiz 2 will be Monday, and it's going to cover 2.2, which was composition. Remember, F composed with G, G composed with F functions. 2.3, which had those word problems like cost, revenue, profit, okay, that we went over, and I made an assignment from. And what we just finished on limits and limits to infinity. Okay? What we're about to start now will not be on the quiz Monday, but we are going to go a little further. Okay? And just so you're aware, I did give this as a take-home that you just turned in. Mondays will not be take-home. It will be in class. I want you to be ready for that. So, if you just look over the homework I assigned from each of those, you're going to be so ready for that quiz and it'll be a good grade. Okay? Practice what we've done in class. Make sure these odd ones that I assigned, you get them right, and you'll be in good shape. Okay, so 2.5. I think I just want to do the first half of 2.5 today, and we'll finish it before our quiz Monday. But on page 126, do you remember I was telling you that for a limit to exist, it has to approach the same number from both sides, right? What if we're now ready to define one-sided limits? Okay? Here is the definition of those in the terminology. Let's see. Okay. L is the left-hand limit of f as x approaches a. If f of x values approach a unique number L as x approaches a from the left side only. Okay? The only difference in notation, and I've written it here, is instead of x approaching a, it's x approaches a with a little minus in the exponent position, which means from the left side only, from the left. Okay. M is the right-hand limit of f as x approaches a. If f of x values approach a unique number m, as x approaches a from the right only. Look at that notation. Limit as x approaches a with a plus in that exponent position. That means from the right-hand side only. Okay? All right. So left-hand limit and right-hand limit. One-sided. I'm going to move it up just a little bit to get this next definition in. The limit as x approaches a, like we did last time, exists if and only if the left-hand limit equals the right-hand limit, and they're the same. Equals that limit. And that's what we were saying last time. If both sides don't approach the same number, it doesn't exist. D and E, right? That's what we have to see. So we'll say we'll find the left-hand limit and the right-hand limit, and if they're the same, the limit as x approaches a exists and is L, that number L.
That plus and minus only tells if it's left or right. It's like
Yes. So if I asked you, like, not on this quiz Monday, but on the next one, to find x as x approaches a plus, that means just from the right. If I put the minus there, just from the left. But if I don't put a plus or minus, like I will on Monday, just the limit, it has to approach the same number for both sides. Okay? And we already saw some of this. Remember some of those piecewise functions where one side went to 2 and the other side went up to 3? It didn't exist, did it? There was a left-hand limit and there was a right-hand limit, but they weren't the same. And that's what we'll be looking for. Okay? So, just to get some of those in our heads, look at number 2 on page 126. And if everybody's got their book, I won't even try to draw these if you don't mind, because they'll be very ugly. Number 2, if you look at the graph in number 2, they want me to find the limit. And in number 2, they say the a value is 3. The limit as x approaches 3 from the left, f of x. The limit as x approaches 3 from the right, and then the limit as x approaches 3. I want to answer all 3 of those parts for that number a. Okay. Tell me from the left, if you get close to 3 from the left-hand side, what is y going to? From the left, it's going to 3, isn't it? Up to that closed eye. What if you approach 3 from the right-hand side? What is y going up to?
5.
It goes up to that open circle at 5, isn't it? Closer and closer and closer. What would you say about this third question? Why is it D and E? Because 3 is not equal to 5. They're not the same. Okay? What would you say about number 4? What's the left-hand limit as you get close to 1?
3.
3. What's the right-hand limit in number 4? 3. What's the limit as x approaches 1? It's 3. It's the same, isn't it? They approach the same number. That's easy, isn't it? Nice? Okay. What would you say about 8? What's the left-hand limit if you get close to 0? 2. What about the right-hand limit as you get close to 0 from the right?
2.
What's the limit as you get close to 0, period? 2. We're agreement. Those are easy questions with the graphs, right? Nice. Okay. What would you say about number 10 if you use the little graph at the bottom of that first column? Number 10, and let me write it up here. 10 says, what is the limit as x approaches 0? Oh, it's just x approaches 0, not from either side, right? I don't think there's a plus or a minus up there. C equals f0. Okay? If you look at that graph, that piecewise looking function, if you get close to 0 from either side, what's it going to? It's going to 3. What is f of 0? 3. Looks to be right. So I guess that would be true, wouldn't it, if we assume that f of 0 is 3. They should have made a closed dot, shouldn't they, so that we could have seen that? But I think we would say 3 for that. It approaches the same number. Approaches 3, which we could call f of 0. What about 12? What is the limit as x gets close to 2 from the right-hand side? 12 says the limit as x gets close to 2 from the right. Well, look at that graph and approach from the right of 2.
1.
If you're approaching 2 from the right, it's in that horizontal piece, isn't it? And what does it approach? It approaches 3, that closed dot at 3. Or, yeah, the closed dot up at 3. So if you get closer and closer to 2 from the right, it goes up to 3, doesn't it? That closed dot. Very good. So that's true, isn't it? What about 14? Limit as x approaches 5 from the left. Does that also go up to 3? It does, doesn't it? You get closer and closer to 5 from the left-hand side, it's going up to that closed dot at 3. So that's also true. They give you some more from 15 to 20 with that other graph. What would you say about number 18? If you approach 4 from the left-hand side, is it 3 or is it not? Is it true or false? Where is it going from the left side as you get close to 4? It's going up to 3, isn't it? So the left-hand limit is 3. What if they would have said the right-hand limit as you get close to 4? If you get close from the right-hand side to 4, it's going to infinity, isn't it? Going up forever. They're not equal, are they? So if they asked you this question, the limit as x approaches 4 with no side on there, what do you say? Left side it went to 3, right side it went to infinity. They're not equal. So it doesn't exist. Okay? Very good. All right. What would you say about 24? Is there any problem at all with 24? 24 says the limit as x approaches 1 from what side? From the right. Of x plus 2 over x plus 1. Does it matter if you're coming from the left or right if it's 1 in this one?
No.
That doesn't make a 0 denominator, does it? So what's my limit? Yeah. Now, if that would have been x minus 1, we would have had to think about it a little bit. All right? But x plus 1, I could just plug that 1 in. Approach it from the right, it would be 3 halves. Approach from the left, it would be 3 halves, wouldn't it? Okay? One that we might have to think about a little more is 26. limit as x approaches 0 from the left. This is where I don't agree with the book's interpretation of these a little bit. Okay? I want you to look at the graph of this and you tell me what you think. If I graph 1 over x, standard measure, what if x gets close to 0 from the left side? Where's y going? That's obvious to everybody, isn't it? If I get closer and closer and closer to 0 on the x-axis, that y is getting smaller and smaller and smaller. So what do we say? 11. I agree with you. You know what the book's going to say in the back for that question? They're going to say D and E. But if we know where it goes, I want you to say where it goes. And there's a theorem that helps us deal with that. And I'm going to show you that theorem. So I just wanted to preface a few of these odd problems. They're going to say D and E in the back for that. I would say negative infinity. Okay?
They're just plugging it in.
By looking at, but see, this is the theorem, and this is going to be good. Let's try one more, and I want to show you how the theorem is going to work. Let's see. What if we did 34? 34 says the limit as x approaches 1 from the right of 1 plus x over 1 minus x. Let's graph it. 1 plus x over 1 minus x. Parentheses. 1 plus x divided by parentheses 1 minus x. Okay. Standard limit. If I get, now look at that question again. The limit as x approaches 1 from the right. If I approach 1 from the right, closer and closer, where's y going? 11. What if I told you that we could figure out that that's negative infinity without actually having to graph it? Would that make you happy? Or not happy, but glad? Okay. Here's what the theorem says for a limit like this. Let me show it to you. Okay. Here it is. To evaluate this limit, just like we saw, if you have limit as x approaches a of a fraction, f of x over g of x, think of them separately. Okay? When the limit of the numerator is not 0, but the limit of the denominator is 0. You saw that that happened in 34? If I let x approach 1 in the numerator, it was 2, wasn't it? But downstairs, 1 minus 1 would have been 0. That's this situation. Here's how you tell, and I hope this makes sense. If the fraction f of x over g of x is larger than 0 as x approaches a, then the limit's infinity. If that fraction is less than 0 as x approaches a, then the limit is negative infinity. Look at the last two we just did according to that. Read that again. If the fraction's positive as x approaches that number, the limit's positive infinity. If the limit's negative as x approaches a, then the limit is negative. Look at the last two we did. This is the way I would say it. Give me a number a little to the right of 1. 2. How about 1.01? You could say 2, but 1.01 is very close to the right of it, isn't it? If I put 1.01 in here, is that fraction positive or negative? It's a positive over a negative, which is negative. Where does it go? I mean negative infinity. I like it. Look at this one. Give me a number a little to the left of 0. Little to the left of 0? Negative 0.001 or something? If I put negative 0.001 in there, that's negative. Where does it go? Negative infinity. See what that theorem does for us? We don't have to graph it. Just put a number a little to that side of the number into your expression and say, well, is it positive or negative? That's where it's going to go. I like that. Try another one. What if we said, how about this one? I could just make one up. Maybe I've exhausted all the clear examples. Let's see. Here's a good one. What if we said limit as x approaches 2 from the right-hand side of x minus 3 over x minus 2? If I put in a number a little to the right of 2, that's like 2.01, that would be a negative over a positive, wouldn't it? Would that go to negative infinity?
Yeah.
Would you agree? Okay. If you weren't sure, what could you do if you didn't trust yourself? Let's try it. If I graph parentheses x minus 3 divided by parentheses x minus 2 on a standard window, if we approach, and what was my question again? It was, if I approach 2 from the right, if I get closer and closer to 2 from the right, where's it going? Backs it right up. But I knew that from that theorem. I knew that since I got a negative result, it was going to negative. Okay. But the bad thing, in your book, or maybe, I don't know if my math lab will do it or not, if they give you this question, a lot of the answers say D and E, and it makes me so angry, because even there's a theorem about it. That's a problem with the book, that I should write them, right? That's not D and E, that's negative infinity. Let's see. Oh, okay. This is good. 30 says, the limit as x approaches 2 from the right of 2 times square root of x minus 2. If you get very close to 2 from the right-hand side, what's that approaching? If I put in a number very close to 2, wouldn't that be 0? What's 2 minus 2? Good. But think about this. What if I change the question? And I said the limit as x approaches 2 from the left. What if I tried to put 1.999 into there to get close to 2? What happens? It's imaginary. I can't do that. So what? I like that being. What if I had no plus or minus out there? What would you say? D and E. Because since this one didn't exist, they would have to be the same, wouldn't it, for it to exist? I'm fine if you come from above 2.01, 2.001, closer and closer and closer. It gets close to 0, doesn't it? But if I try to approach from below, from the left-hand side, I can't put 1.999 in there because it's imaginary. So that would not exist. So you might just, for completeness, want to say the limit as x approaches 2 with no symbol of 2 square root of x minus 2 also does not exist. because they are not equal. Okay, great. Good. Okay. So you would agree with me that number 36, if you approach -3 from the right-hand side, is going to be okay. But what if you tried to approach -3 from the left? That would not exist because it would be imaginary. But if you approach from the right, if you put in -2.999, that's getting very close to 0, isn't it, in the numerator? Which would override everything if it's 0. Okay? So to finish up today, let's look at 38. What if they gave you a piecewise function? This is exactly where I wanted to get to today. So I think we did this. They give you this piecewise function. F of x is -x plus 1. X is less than or equal to 0. And 2x plus 3 if x is greater than 0. The questions are, find the limit as x approaches 0 from the right, and the limit as x approaches 0 from the left. Yes. And I might add just a third one for completeness. The limit as x approaches 0, period. If you're going to approach 0 from the right-hand side, which piece do I use, the first piece or the second piece? If I'm coming from above 0, I would have to use this piece, wouldn't I? If you get close to 0, what's the limit? If you get close to 0 from the left, which piece? Top one. If you get close to 0 in that piece, what's the limit? So what do you say about the limit as x approaches 0? Because they are not equal. That's not bad, is it? If you didn't trust it, you could do that piecewise graph on your calculator, and you would see that one side goes, from the right it goes up to 3, and from the left it goes to 1. They're not the same. Okay? The assignment so far, even though it's not on your quiz on Monday, go ahead and try these so we can talk about them. What about page 126? 1 through 37. Make sure you practice these and check your answers to make sure you got it right in your head. The only trouble I would have is some of those later ones, like I said, where it says D and E, I would disagree with them for a few. But just go ahead, and if you have questions, we can go over them. But try to be ready for this. Remember, what was it? It was composition of functions, cost, profit, revenue, supply, demand, applications, and the initial limit section. Questions?
Do we have to know each of those formulas? Like, do we have to memorize those?
Basically, in the supply and demand, I give you the functions. But in the cost perfect revenue, I want you to be able to form it like that number 18 I did on the board that assigned you 17. So I won't give you anything. Just be able to form it like in the homework, and you'll be good. I'm not straying from it too much at all. In that section 2-3, like number 17, you can get that right, you can get the whiskers. All right? Have a good one. Let me know if you have trouble. But you're taking limits a lot better than most semesters in this class. You know, we used to have mass chaos at limits, didn't we? All right.
Desperate looks of confusion.
The place that I was talking about earlier, Cape Sandbox.
Cape Sandbox.
Yeah. Not Blast, but Blast.